Hello everyone, welcome to my video. And my name is Akash Patel, and this is the video in our machine learning model evaluation series. So, so today's presentation is ROC curve, AUC, precision recall curve, and regression metrics such as MAE, RMSE, and R squared. So these concepts help us evaluate machine learning model in even greater detail and help us choose the right model for different real world problems. So although some of these topics may sound complicated at first, I will explain each one using simple language and practical examples so they are easy to understand. So let's begin. So in our previous video, we evaluated the model using metrics such as recall, precision, specificity, and F1 score. So these metrics are calculated after the model had already made its final predictions. However, many machine learning models do not immediately predict yes or no. Instead, they first calculate a probability score. For example, a fraud detection model might estimate that one transaction has an 82% chance of being fraudulent, while another transaction has only 46% chance. So the model then compared these probabilities with a decision threshold to decide whether the transaction should be classified as fraud or not fraud. If we change these thresholds, the model's predictions also change. Lower thresholds makes the model classify more transactions as fraud, while a higher thresholds make the model more selective before predicting fraud. Because the predictions change, the confusion matrix also changes. As a result, evaluation metrics such as recall, precision, and positive rate can also change. Instead of evaluating the model at only one threshold, machine learning engineers often study how the model performs across many different thresholds values. So this is where ROC curves and precision recall curves become very useful. So let's start by understanding the ROC curve. So ROC curve stands for receiver operating characteristics. Through although the name sounds technical, the main idea is actually quite simple. So ROC curve shows how the performance of classification model changes when we adjust the decision threshold. Instead of looking at only one prediction's results, the ROC curves allow us to see the model performance across many different thresholds value. The graph compared two important measurements. At the first is true positive rate, which is the same as recall and tell us how many actual positive cases the model correctly detects. The second is the false positive rate, which tell us how many actual negative cases are incorrectly predicted as positive. Each point on the ROC curve represents the model's performance at a different threshold. As the threshold changes, both the true positive rate and the false positive rate also change, creating the curve. In general, a better model produce a curve that stay closer to the upper left corner of the graph because that means it detects more positive case while keeping false alarm as low as possible. The diagonal, diagonal line represents a model that performs one better than random guesses. So the further the curve moves above the diagonal line, the better the model's overall classification performance. Now that we understand what the ROC curve represents, let's see why changing the thresholds create this trade-off between detecting more positive cases and creating more false alarms. So now that we understand what the ROC curve is, let's see why changing the decision thresholds may affects the model's performance. Imagine our fraud detection model gives every transaction a probability scores between 0 and 1. If we set a high threshold, the model become very useful before predicting fraud. It will only classify transactions as fraud if it has a very high probability. This approach usually reduces the number of false positives because the model is less likely to incorrectly label normal transactions as fraud. However, there is also disadvantage. Some real fraud cases may not reach that high threshold, so the model misses them. So these missed cases become false negatives, which means the true positive rate or recall decreases. Now let's imagine the opposite situation. If we lower the threshold, the model becomes less strict. It start predicting more transactions as fraud. As a result, the model usually catches more real fraud cases, so the true positive rate increase. This is called the ROC trade-off. The goal is not to find one threshold that work every situation. Instead, the best threshold depends on the application. This is exactly why ROC curves are useful. They allow us to study the model's behavior across many different thresholds before deciding which one is the best. So the next concept is AUC, which stand for area under the curve. As the name suggests, AUC measures the total area underneath the ROC curve. Instead of looking at every point on the graph separately, AUC summarized the model's overall performance into a single value. A simple way to think about AUC is that it tells us how well the model can separate positive cases from negative cases. A model with a higher AUC is generally better at distinguishing between the two classes. For example, an EUC of 1.0 represents a perfect classifier. This means the model correctly separates every positive cases from every negative case. On the other hand, an EUC of zero point 0.5 means the model performs about the same as random guessing because it cannot reliably distinguish between the two classes. Although a higher EUC usually indicates a better model, we should not rely only on this single value. EUC tell us about the model's overall ability across many thresholds because but it does not tell us which threshold is best for a specific business problem. For example, two models may have a similar UC value, but one may still be more suitable depend on whether the organization want to reduce false positives or detect more positive cases. So EUC is an excellent metrics for comparing model, but it should always be considered together with the goals of the applications. So now suppose we have two different machine learning models, so both are designed to detect fraudulent transactions. The question is which model performs better. One way to answer this by comparing these ROC curves and AUC value. Imagine the model A has an ROC curve that stay closer to upper left corner of the graph than model B. This tells us that across many different thresholds value model A is generally better at detecting fraud while keeping false alarm lower. If model A also has a higher EUC, it suggests that the model has a stronger overall ability to separate fraudulent transactions from normal ones. However, choosing the best model is not always the simple. Even if one model has a slightly higher EUC, the model decision should also consider the need of the business. For example, if a company has only a small team to investigate fraud alert, it may refer a model that produced fewer false positives, even if another model has a slightly higher EUC. So AUC help us compare the overall performance of different models, but the final choice should always consider the real world problem the model is trying to solve. So now, so far, we have learned how the ROC curve help us evaluate a classification model across different decision thresholds. However, ROC is not the only evaluation tool available. In some situation, another graph called the precision recall curve or PR curve can provide even more useful information. The precision recall curve focuses on two metrics that we learned in the previous video, precision and recall. Instead of showing the relationship between the true positive rate and false positive rate, this graph shows how precision changes as recall changes when the decision threshold is adjusted. Think about our fraud detection example. If we lower the decision threshold, the model usually detects more fraud cases, which increase recall. However, it may also classify more normal transactions as fraud, causing precision to decrease. On the other hand, if the increase the threshold, the model become more selective. Precision may improve because the fraud alerts become more reliable, but recall may decrease because some real fraud cases are missed. The graph becomes especially useful when the positive cases is rare, such as fraud detection, disease diagnosis, or identifying network attacks. In this situation, we often care much more about how well the model find positive cases than a simple measuring overall performance. At this point, you may be wondering which graph is better, the ROC curve or the precision recall curve. So the ROC curve gives us a broader view of how well a model separates positive and negative classes across different threshold value. The precision recall curve, on the other hand, focus only on precision and recall. It tells us how well the model detects positive cases while also showing how reliable these positive predictions are. For example, in a fraud detection, most transactions are normal while only a small number are actually fraudulent. So instead of asking which graph is better, is more useful to ask which graph is more appropriate for the problem you are trying to solve. Many machine learning engineers actually examine both graphs before making final decision about a model. So let's move to the next slide. So far in this three video series, almost everything we have discussed has focused on classification problems. In the classification, model predicts categories such as fraud or not fraud, spam or not spam, and disease or no disease. Now we are moving to different types of machine learning problems called regression. Unlike classification, a regression model predicts numerical value instead of categories. For example, a regression model can predict the price of a house, a monthly sales of the business, the delivery time for an order, or the future demand for a product. So because the model predicts numbers instead of classes, we can no longer use a confusion matrix or classification matrix such as precision and recall. Instead, we need evaluation methods that measure how close the predicted value are to actual value. Rather than counting correct or and incorrect classification, regression focus on the size of the predictions error. This is why regression use different eva- evaluation metrics, including MAE, RMSE, and R squared. In, in the next slides, we will learn each of these metrics measure how they help us evaluate regression model. So now we understand the difference between classification and regression. Let's learn our first regression evaluation metrics called MAE, which stand for mean absolute error. So MAE measures how far the model's predictions are from the actual values on average. The word absolute is important because it means we only care about the size of the error, not whether the predictions is higher or lower than the actual value. Let's understand this with a simple example. Imagine we have a machine learning model that predicts house prices. Suppose the actual prices are uh, 3,000 $3 lakh and 4 lakh dollar and 5 lakh dollar, while the model predicts 2 lakh 800, 800, 4 lakh 30, and 4 lakh 90,000. The prediction error are 20,000, 30,000, and 10,000. To calculate MAE, we first take the absolute value of each error, then add them together and finally divide it by the number of predictions. So the result is 20,000. So in the simple word, this means the model's predictions are about $20,000 away from the actual price on average. One reason MAE is popular is because it is very easy to understand. So if the model predicts house prices, the error is also measured in dollar. If the model predicts delivery time, the error is measured in minute or hours. This makes MA easy to explain even to people who do not have the machine learning background. However, MA treats every error equally, whether it is small or large. So the next regression matrix is RMSE, which stands for root mean square error. So like MAE, RMSE also measure the difference between the predicted value and the actual value. Instead of using the absolute value of each error, RSME squares each error before calculating the average. After finding the average, it takes the square root so that the final result is expressed in the same unit as the original data. You don't need to memorize easy mathematical step. The most important idea is why we square the errors. So when the error is squared, larger error increase much more the smaller ones. For example, in one house price example, error of 30,000 has a much greater effect on RMSE than an error of 10,000. This means RMSE pays much more attention to large mistakes. Because of this, RSMA often used when large predictions error are especially costly or risky. For example, if a company predicting future sales or electricity demand, one very large predictions error could have a much bigger impact than say several small ones. So while both MAE and RMSE measures predictions error, MAE treats every error equally, whether RMSE gives extra importance to large errors. Now let's learn one more regression matrix that measures model performance from the different perspective. So one final regression evaluation matrix is R squared, also written as R squared. Unlike MAE, RSME ASCII does not measure the average prediction error. Instead, it tells us how well the model explains the relationship between the input data and the actual outcomes. In simple words, R squared tells us how well the model fits the data. A value closer to 1 generally means the model explains the data very well and its predictions closely follow the actual pattern. At the value close to 0 means the model is not explained the very well and performs only slightly better than using a simple average. In some situations, the value can even become negative, which means the model performs worse than using the average of the actual value as a predictions. So instead, it gives us the overall idea of how well the model fits the data. So because each regression matrix measures something different, machine learning engineers often used R squared together with MAE or RMSE instead of depending on only one matrix. So this provides a more complete understanding of the model's performance. So now we have learned about both classification matrix and regression matrix. An important question comes up: so which evaluation matrix should we use? So the answer is simple. There is no single matrix which is best for every machine learning problem. The right matrix always depend on types of predictions we are making and the goal of application. If the model predicts categories such as fraud or not fraud, then it is classification problem. In this case, we used metrics like precision recall, F1 score, ROC curve, AUC, and the precision recall curves. If the model predicts numerical value such as house prices or monthly sales, then it is regression problem. For this model, metrics like MAE, RMSE, and R squared are more appropriate. After identifying the problem types, we should think about the real world objective. If missing positive case is the biggest concern, the recall become very important. If reducing false alarm is priority, then precision is often the better choice. If both precision and recall are equally important, then the F1 score provide a balanced evaluation. For regression model, MA is useful because it tells us average predictions error in a single unit, while RMSE gives more important to larger error. R squared help us understand how well the model fits the data. The most important lesson is that we should never choose a metric just because it has the highest value. Instead, we should choose the metrics that best matches the purpose of the model and the real world problem we are trying to solve. So let's review everything we have learned throughout this three video learning journey. So before we finally finish this presentation, let's take a moment to review the main idea for overall the video. In the first video, we learned the evaluating a machine learning model required much more than simply checking the accuracy. We explored the confusion matrix and learned how very predictions become either a true positive, true negative, false positive, or false negative. In the second video, we used these four outcomes to calculate important evaluation metrics such as recall, precision, specificity, and F1 score. And today's presentation, we expanded our understanding even further. We learned how ROC curve and AUC help us evaluate model performance across different decision thresholds and how precision recall curve become spe- specifically useful when the positive cases are rare. We also explored regression evaluation, learned how MAE, RMSE, and R squared help us measure prediction errors and overall model performance when predicting numerical values. Instead, different metrics answer different questions and selecting the right one depending on the type of model, the data, and real world problem we are trying to solve. So as we continue learning machine learning, these evaluation techniques will help us compare model more effectively and make better decisions when developing real world AI system. So this is bring us the end of my presentation. Although these three videos we explored a complete journey of machine learning model evaluation, we started by the understanding of confusion matrix. We learned how to calculate and interpret precision, recall, specificity, and F1 score. Finally explored advanced evaluation techniques such as ROC curve, AUC, precision, recall curves, MAE, RMSE, and R squared. I hope this presentation helped make these concepts easier to understand and showed how choosing the right evaluation metrics can lead to better machine learning decision. I would like to sincerely thank my professor Dr. Govinda Swami for his continuous guidance, encouragement, and support throughout this journey. His practical teaching approach has helped me better understand machine learning concept and their real world applications. So thank you so much for taking the time to watch my presentation. Once again, thank you for watching. Have a wonderful day.